All right, here recording in progress. So share the screen. All right. Whoops. Just in focus here. Okay, change in the homework. Okay, I decided to skip 37. It was a much harder problem involving greatest integer function. I want you to know something about the greatest integer function, but not to the extent that the book goes over. I'll talk a little bit about the greatest integer function today. Okay, I also totally botched question 15, so I've decided to throw it out. So skip problem 15. I botched that up. So just throw that out. Okay. And we're here. So on schedule, knock off 2.2, start a little bit of 2.3. Okay, I think I'll be able to do that right now. Okay, just a quick review of what happened yesterday. Okay, about 25, it was completing a square problem. F of x equals x squared minus 6x plus 7. So let me quickly review something about that somebody asked for. So to complete the square, you take half of -6, which is -3, and square it. -3 squared is 9. So you add 9 and quickly subtract 9 at the same time. So that gives me x minus 3 squared minus 2. So that tells me the vertex is at 3, -2, because it's a translation of 3 to the right and 2 down. So 3 right and 2 down for that one. So that was a problem 25. That's not the, oh yeah, that is 25 right here for that one. Okay. All right, and then the square root function. Okay, you should know a rough sketch is like this. And by the way, if you want to just put a rough sketch on your cheat sheet, your next formula sheet, you may. Okay. But square root function, okay, the domain is bracket 0 to infinity. In other words, only positive numbers, right? Positive and 0, you're not allowed to put in any negative. And the thing that comes out, is also only non-negative quantities. So I just have a first quadrant view here, meaning no second quadrant, no third quadrant, no fourth quadrant necessary. Okay, so I made a table of quote unquote nice values. Square root of 0 is 0, square root of 1 is 1, square root of 4 is 2, square root of 9 is 3, square root of 16 is 4, and so on. Yes, there is a square root of 2, there is a square root of 3, they're not nice, they're irrational. And there is a square root of 5, 6, 7, and 8, they're not nice. I mean, you can punch it in your calculator if you wish, but you know, don't really feel like doing that. Okay, so I plotted 0, 0, 1, 1, 4, 2, 9, 3, 16, 4, and it curves like that. So that's a quick sketch of the square root function. Okay, and then I just want you to have a knowledge of what the greatest integer function is. Okay, so we talked about that a little bit the other day. Okay, it's kind of a messy function. Greatest integer function, sometimes called the floor function. Okay, and defined for a given real number x to be the largest integer that is less than or equal to x. Think of it as a rounding down. No matter what the number is, you round down. If you already have an integer, you leave it alone. If you have any fraction or decimal part, you always round down. Okay, so I'll give you some examples here. So I made up my own examples. And I'll just go ahead and add. Our book does that. Some books uses this, the brackets, for greatest integer function. Now, f of x is the same as x if x is an integer. And what are integers? Integers are -3, -2, -1, 0, 1, 2, 3. Okay, so they're the whole numbers and their opposites. If x is not an integer, always round down. So you do not round off. You always round down to the nearest integer. Okay, so here are some examples. The greatest integer function of 3 is still 3. Greatest integer of -4 is still -4. So if you already have an integer, leave it alone. If you have any fraction or decimal part, you always go down. So greatest integer function on 3.8 would be 3 because you round down. You do not round off. You always go down. So you don't change this to 4. Leave this 3. Greatest integer function on negative 2.7 is negative 3. Greatest integer function on 5 and 99/100. And this is really, really, really close to 6, right? But it doesn't make any difference. Any fractional part, you always go down. So the greatest integer function of 5 and 99/100 isn't 6. It's going to be 5. You always have to go down. And greatest integer function on negative pi. Negative pi is like negative 3.14159. And again, going down would be negative 4. Okay. And of course, that's the reason why the graph looks like it does. So I mentioned the other day, greatest integer function of integers is itself. So closed circle, closed circle, closed circle. So that's 0, 0, 1, 1, 2, 2, 3, 3, negative 1, negative 1, negative 2, negative 2, negative 3, negative 3, right? And what's happening here? If I take any number between 0 and 1, counting 0 but not counting 1, all of those would get mapped down to 0, greatest integer function. So the greatest integer function on 0.1, 0.2, 0.3, 0.4, I'm moving my pen along with it, 0.5, 0.6, 0.7, 0.8, 0.9, 0.999, 0.99999, all of those would have a greatest integer value of 0. And then once you reach 1, it jumps up to 1. Greatest integer function on 1 is 1. And then 1.1, 1.2, 1.3, 1.4, 1.5, 1.9, 1.99, 1.999. These would all map you down to 1. And then once you hit 2, it jumps up again. So you have the step function, so to speak. So it looks like a bunch of steps. The domain is all real numbers, but the range is only integers, which makes sense. The only thing that you can come back with is integers. Okay, so I'll just say the domain is all real numbers, funny looking R, but the range is a set of integers. The only thing that you can come out with is an integer. Right? All right, then let's see. A couple more that I wanted to show you from the assignment. F of x equals absolute value of x minus 4, as an example. So you take the regular absolute value function. This translates 4 units to the right. Translate. Again, the English word translate in mathematics means to move. Okay, of course, we have the other meaning of translate, like translate a language, but there's also a dictionary definition of translate, which means to move it left, right, up, down, forward, or backward, or whatever. So if I change x to x minus 4, that translates 4 to the right. So 0, 0 becomes 4, 0. Okay? And a double check, what happens when you plug in 4? You get 0. But notice if I moved over here, move it 4 to the left, you have negative 4, 0. But if you plug in negative 4 here, you don't get 0. Right? So that's kind of a double check that you plugged it in the right way, and so on. Okay. All right, and yeah, go back and number 3. So you should know your basic absolute value function is V-shape, going through the origin. Okay, absolute value of x plus 2 minus 2, all right? So that moves 2 to the left, 2 down. Okay. So the corner point, if you want to call it a vertex, I suppose, used to be 0, 0. 0, 0 gets translated to negative 2, negative 2. So I just come down to negative 2, negative 2, and then draw my V shape. So it ends up looking like that. Now, 35, I'm going to skip C. So 35 skips C. At f of x equal x plus 1, sketch the graph of f of x on the interval from 0 to 4. Well, that's easy. Slope is 1, y-intercept is 1. So it goes up something like that. Okay, a little bit harder was part B. Let A of t denote the area of the region bounded by the x-axis, the y-axis, the curve y equals f of x, and a vertical line x equals t. Find an expression for A of t, and sketch the graph of y equals A of t on the interval from 0 to 4. Okay, so we are going to just do this part. So I'm going to cross this out. Find an expression for A of t. So this is the picture. So y equals x plus 1 comes like this. So I'm finding the area of this trapezoid. Okay. Remember in geometry, this is sometimes called a trapezoid. It's a four-sided figure that has one pair of opposite sides parallel, but the other is not parallel. Okay. So I want to try to find this area here, and this is t. Well, if this is y equals x plus 1, if this is t, this as a point is t comma t plus 1. So how do I find the area? Well, I break it up into this rectangle and this triangle. So this rectangle, the height is 1, the length is t. So the area of this, I know it looks like a square. It's in general, it's a rectangle. So the area is length times width, so t times 1. This is t by t. The area of a triangle is 1/2 base times height, so 1/2 t times t, t squared. Okay, so an expression for the area is 1/2 t squared plus t. 1/2 t squared plus t. Okay, and then, yeah, 27, 29, and 31. I think it's too much to make you graph the whole greatest integer function. It's kind of clumsy. So I'm going to change it so you just have to describe what happens. Okay, it's already hard enough to just draw it as it is. Then you have to take this thing and move it 2 to the left or 2 up and so on. It's very, very clumsy. Okay, so I'm going to change the directions to just describe what happens. Okay, I have to get this thing focused again. There you go. So you don't have to graph it. This is what it looks like. But just describe what happens. So 27, 2 to the right. Okay. So 27. Move 2 to the right. So if you know that's what happens, that's all you really need to know. But to actually physically do that, you know, to move that over 2 and move that over 2, that's very clumsy. And let's see, this one. 1 to the left, 2 down. Okay, so 29, 1 left, 2 down. And finally 31, 2 minus greatest integer value. Okay, so first, if I replace x with negative x, that reflects across the x-axis, and that moves it 2 up. So let's say for 31, reflect across x-axis, and then 2 up. Reflect across x-axis, and then 2 up.
Wouldn't it be the y-axis? Because x could still be positive. It's really the y that's turning negative. Because it's negative, greatest integer x plus 2.
It's the opposite of the greatest integer function. Right, so the opposite of the greatest integer function reflects across the x-axis. A reflection across the y-axis would be if the negative were inside the function there. So in other words, the first thing that happens is reflect right there. So all of these gets bounced down and all of these get bounced up. And then you move the whole graph 2 up. Okay. So this should be okay. That's it for that one. Okay. All right. So I think that's as much as I was going to show you for section 2.2. I'll introduce some of the next section 2.3, which is on arithmetic combinations of functions. On page 93. These are fairly easy. So you're given two functions, add, subtract, multiply, and divide them. It's just like adding, subtracting, multiplying, and dividing any other function. So f plus g means f of x plus g of x. F minus g, f of x minus g of x. F times g, f of x times g of x. F divided by g. You could write it like that too, f of x divided by g of x. Okay, so you're just putting functions together, as it were. Okay. What gets a little bit harder is when you have, whoops, is when you have a composition of functions, and I'll show you that when we get to it. So 2.3, the assignment was 1 to 21 odd. Okay. It's 1 to 21 odd. And let me show that to you. Page 100. Side note, hard to believe we've already had 100 pages of math in this semester. Seems like we just started, but already 100 pages anyway. Okay, that shows you up to 7. And then on page 101, there's that, and up to 21. Okay, all that's happening is we're adding, subtracting, multiplying, and dividing. Just literally add, subtract, multiply, and divide. Okay. And then it says something about the domain. So that might be the hardest part of it. But as far as computing the sum, difference, product, or quotient, that should not be that big a deal. Okay, so I'll show you a couple of those. Okay, so 2.3. F of x is 2x, g of x is x squared plus 1. Right? So they're asking you to add, subtract, multiply, and divide. It's really not that big a deal. So f plus g, just add them up. 2x plus x squared plus 1, or you can rewrite it, x squared plus 2x plus 1. Domain is all reals. F minus g. So that minus that. In parentheses, 2x minus parentheses, x squared plus 1. So it's 2x minus x squared minus 1, negative x squared plus 2x minus 1. And the domain, again, is all real numbers. Okay. By the way, you might say, well, when is it not all real numbers? Well, when you have to divide by something, you know you can't divide by 0. You can't take the square root of a negative. Later on, we'll do some log stuff and trig stuff. There's some limitations on logs and trig. But if you just have a polynomial, then domain is all real numbers. F times g, just multiply them. That times that, 2x times x squared plus 1, 2x cubed plus 2x. And again, in domain is all real numbers. F divided by g, that divided by that, 2x divided by x squared plus 1. Aha, sorry. Now, what about the domain? I put all rules, but maybe I shouldn't have shown it to you ahead of time. We have to ask ourselves, okay, there's a division. I know I'm not supposed to divide by 0. So I have to throw out any value which makes the denominator 0. But stop and think about it. X squared plus 1. When is that going to be 0? It's never going to be 0. Because you have x squared, right? X squared is non-negative, which means either positive or it's 0. If I plug in 0, I get 0, right? If I plug in any other number, positive or negative, it would be positive. But now if I add 1, it's dead sure going to be positive, which means the denominator isn't going to be 0. So again, the domain is all real numbers. Okay, so that's a little bit tricky. All right, so that was number 1, which is a little bit easier. I'll do a harder one, and then maybe that's all we're going to do for today. So we might be finished somewhat early today. Aha, square roots, much tougher, because I cannot take the square root of a negative, right? So f of x is square root of x plus 1. G of x is square root of 3 minus x. F plus g, I just add them up like this. And by the way, in case you're wondering, no, you're not allowed to combine these. In other words, don't go x minus x is 0, combine it. Don't go 1 plus 3 is 4. That's not allowed. So you're not allowed to, combine something from one radical with the other radical and add them or subtract them or whatnot. Okay, so just leave it like that. Now, how do I find the domain? Well, we know that the square root of anything has to be greater than or equal to 0. So x plus 1 is greater than or equal to 0. And this thing, 3 minus x, also greater than or equal to 0. Okay, a little bit of algebra. This is x is greater than or equal to negative 1. And if I add x to both sides, 3 is greater than or equal to x, which says the same thing as x is less than or equal to 3. Okay. So I put them together. I want x to be greater than or equal to negative 1, but less than or equal to 3. That's everything here. So the domain is bracket negative 1, 3 bracket. Include negative 1, include 3, and the stuff in between. But nothing else, nothing way out to the left, nothing way out to the right is in my domain. So for instance, problem's finished, but 4 is not allowed. Let's see, why is 4 not allowed? Yeah, you can't plug in 4 here, right? Because 3 minus 4 would be a negative 1, and you can't take the square root of negative 1. And let's see, negative 2 is not allowed. So negative 2, yeah, negative 2 is not allowed here. Because then you'd have negative 2 plus 1, which is negative 1. So again, you're taking the square root of a negative, and that's a mathematical no-no. Can't do it, right? Okay, f minus g, well, the only difference is I put a minus sign. So instead of that plus that, is that minus that. All this algebra is identical, so it has the same domain. Bracket negative 1, 3. How about f times g? You multiply them. Okay, now we do have a property of radicals that you can multiply the radicals. So it is okay to say radical this times this, square root of x plus 1 times 3 minus x, provided both of these are greater than or equal to 0. Okay, and we have to do that sign chart business again that we've seen before, right? So my boundary numbers are negative 1 and positive 3. They're both closed, right? From here. And region 1, region 2, region 3. Region 1, I picked negative 2. Region 2, I picked 0. Region 3, I picked 4. Plug in negative 2. Negative 2 plus 1 is negative. Let's see, 3 minus a minus 2, 3 plus 2, positive. So negative times positive is a negative. Is a negative greater than or equal to 0? No, that's false. 0. 0 plus 1, positive. 3 minus 0, positive. Positive times positive, positive. Positive greater than or equal to 0, that's true. Shade in region 2. Region 3, 4. 4 plus 1, positive. 3 minus 4, negative. Positive times a negative is a negative. Negative greater than or equal to 0, no, that's false. So I just have this. So again, the domain is bracket -1, 3 bracket. So far, all these f plus g, f minus g, and f times g all have the same domain, bracket -1, 3. For division, f divided by g, f over g is just that divided by that. And yes, we have a property of radicals that I can put the whole thing under 1. So square root of x plus 1 over 3 minus x. So the thing behind my finger is greater than or equal to 0. The analysis comes out to be exactly the same, except 3 is no longer allowed because 3 in the denominator gives me a 0. Okay? So you can do your sign chart just like over here. It'll be almost identical, okay? Except -1 closed circle, 3 open circle. Because if you plug in 3 minus 3 is 0, you're never allowed to divide by 0. Okay? And do the same analysis, you get the exact same regions being shaded in. So for the last one, f divided by g, the domain is bracket -1, 3 parenthesis, like that. Good. All right, so that's the way that one goes. Why, yeah, plenty of time. I think I'll do 7, then maybe I'll stop with 7. Mention that quickly. 7 is piecewise defined. F of x is -1 if x is less than 0, 1 if x is greater than or equal to 0, and g of x is 1 if x is less than 0, and 0 if x is greater than or equal to 0. Okay, so you have to break it up into 2 parts. What happens if x is less than 0? What happens if x is greater than 0 or greater than or equal to 0? F and G. Okay, F plus G. So F plus G. Here's the part that's less than 0. All right. Let's see if I can get another pen here. I basically add these. If x is less than 0, -1 plus 1 is 0. Then x is greater than or equal to 0. Right? Greater than or equal to 0. 1 plus 0, which is 1. Okay, so one more time. F plus G. If I'm less than 0, I only look at these two. Less than 0, less than 0. -1 plus 1, 0. If I'm greater than or equal to 0, I look at these two guys. 1 plus 0 is 1. Domain is all reals. F minus G, same thing. So if I'm less than 0, only look at this and this. It's -1 minus 1. -1 minus 1 is -2. And then if I'm greater than or equal to 0, that's this one and this one. I subtract because it says F minus G. 1 minus 0, 1. And again, that's defined for all real numbers. F times G, FG, multiply. So the ones that are less than 0, that one and that one, multiply. -1 times 1, -1. How to get 0 over here? Greater than or equal to 0, greater than or equal to 0, multiply. 1 divided by 0. Oh, sorry, 1 times 0. 1 times 0 is 0. Domain is all real numbers. Okay, then finally, f divided by g. F divided by g. Divide -1 divided by 1, -1. If x is less than 0. Greater than or equal to 0. Divide 1 divided by 0. 1 divided by 0. Can't do it. Undefined. Which means in reality, I cross it out. So this function is only defined from -infinity to 0, which is another way of saying negative numbers. Only negative numbers are allowed. Okay. So that is that. Okay, folks, so I'm just about done. I was going to introduce the reciprocal function and then I'll quit. Go from there. So we'll talk about the graph of the reciprocal of a function now. Page 98. This is a little harder. But let me just show you the basic reciprocal function. Y equals x and y equals 1 over x. Okay, we know y equals x looks like this. Okay. Hopefully in your past experience, you've graphed 1 over x. It looks like this and looks like this. It's a reciprocal function. Okay, some things to notice about this. What's the reciprocal of 1? Still 1. And what's the reciprocal of -1? -1. So the graphs touch at 1, 1 and -1, -1. Now, let's think about, I plug in bigger and bigger numbers. 2, 3, 4, 5, right? You get 1/2, 1/3, 1/4, 1/5. Plug in a super big number like 1,000,000, you have 1 over 1,000,000. So when x gets big, y gets small. It gets very close to the x-axis as an asymptote. On the other hand, what happens if I plug in a small number? You might recall the reciprocal of a small number is a big number. Like if I plug in 0.00001, I get a super big number, right? Just demonstrate on a calculator maybe. Let me get this correct here. Show you on my calculator. 1 divided by a super small number is a big number. Well, it switches over to exponential notation. Okay, this is 1,000,000, essentially. I typed in 1 divided by 0.001. It's 1,000,000, essentially. Maybe I'll try to show you one that doesn't have that much stuff. That's a little bit better. 1 divided by 0.0001 is 10,000. So if you divide by a small number, you get a big number. And this graph exhibits origin symmetry. I have symmetry with respect to the origin. So this thing reflects down to here. That means if I replace x with -x and y with -y, I get an equivalent equation. Okay, so there's symmetry with respect to the origin. So the red graph is a reciprocal function. So we'll talk more about the reciprocal function next time. But the reciprocal of 1 is 1. The reciprocal of -1 is -1. And by the way, they keep the same sign. The reciprocal of a positive is positive. The reciprocal of a negative is negative. And when one goes up, the other goes down. So look right here. If I plug in a super big number, the reciprocal is super small. And likewise, if I plug in a super small number, the reciprocal gets real big. And same concept applies over here. Okay. But other than that, I was going to be done for the day. Okay. So I'll let you ask any questions now. Let me stop the share in case anybody wants to put something in the chat. But otherwise, that was as much as I was planning to cover today. Okay, so any questions? Yes.
I was looking over that during the weekend. My only question was, I watched some videos and the y-intercepts when using a trying to get a reciprocal graph. I noticed that you take the y-intercept of the original graph and you keep the x value, but you take the reciprocal of the y value, and it like in the video saying it always goes through that point. And I was just wondering, like, do you just keep Is there anything like, do you know what I'm talking about? Is there anything else I should know about that? The only thing I can think of is that you keep the X value because it's the y-intercept. Does that make sense?
Okay, well, for the y-intercept, you actually don't necessarily keep the values. It depends on what the value is.
Yeah.
But so you're talking about, let's say, oh, I don't have my shared screen back on, so I got to share the screen again. Did you want to look at this perhaps? Or that's not what you're interested in?
No, I was actually watching a teacher lecture about it because I was a little confused. And he said like I believe the y-intercept was -2, right? 0, -2. And then he's like, okay, now take the reciprocal of the y value, which -2 is -1/2. And the graph goes through 0, -1/2, the reciprocal graph.
Correct. That's correct.
That's correct. Okay. I was just trying to clarify about that because I was a little confused. Thanks.
Okay. For everybody else, if you don't understand what we're talking about, it doesn't apply right now. We'll get to it later. But yeah, it's probably better if you don't worry about what we were just talking about. Okay. For everyone
Sorry.
else. No, that's okay. Right. We're going to get to all this tomorrow about the reciprocal of a function. So yeah. But a lot of this piggybacks off of this right over here. Okay. All right. Anybody else? I have to stop the share again in order to see the chat. Okay. I don't see anything else in the chat. Okay. Any other questions, please? Otherwise, we're going to call it a day. All right. I don't see or hear anything. So that's it. All right. Have a good day, everybody. And we'll see you next time.
Thank you.
All right. Bye, everybody. All right.